Hello everyone, I welcome you all to this class. This is linear algebra class, and today we'll be solving this example under this topic, diagonalizable matrices. Now we say that a square matrix A is diagonalizable if you can find an invertible square matrix P and a diagonal matrix D such that this diagonal matrix D will be equal to P inverse AP. So if you can find an invertible square matrix P such that P inverse multiplied by A multiplied by P will give you a diagonal matrix D, then this square matrix A will be said to be diagonalizable. So this means that this square matrix is said to be diagonalizable if it is similar to a diagonal matrix D. So in this example, they asked us to find that matrix P such that P inverse AP is a diagonal. We'll give you a diagonal matrix, and then we are giving this matrix A on the board here. Now what we are going to do is we are going to compute the eigenvalues of this matrix A and get their corresponding eigenvectors. Then this matrix, the eigenvectors will form the columns of this matrix P. With that, we'll get our matrix P. So let's start the solution. So to get the eigenvalues, you evaluate this determinant of A minus lambda I and equate it to 0. And this implies determinant of your A is the matrix with the entries given on the board. Your lambda is a scalar, and your I is the identity matrix. It will be 2 by 2 because your matrix A is 2 by 2. So this is the identity matrix, determinant equated to 0. So this simply implies determinant of, let's write our matrix A first. Then minus. So what you are going to do is you are going to use this lambda to multiply this identity matrix, right? So let's multiply. Lambda multiplied by 1 is lambda. Lambda multiplied by 0 is 0. Lambda multiplied by 0 is 0. Lambda multiplied by 1 is lambda. Determinant equated to 0. So we can subtract, right? So let's subtract 2 minus lambda, 2 minus lambda, negative 1 minus 0, negative 1, negative 1 minus 0, negative 1, 2 minus lambda, 2 minus lambda. Determinant equated to 0. And this implies, so we have 2 by 2 matrix to, we have the 2 by 2 matrix to multiply. So we multiply the entries of the principal diagonal. That's 2 minus lambda multiplied by 2 minus lambda. Then you subtract the product of the other diagonal. Negative 1 multiplied by negative 1 is what? Positive 1. Equated to 0. So this implies we can expand, right? 2 multiplied by 2, 4. 2 multiplied by negative lambda, negative 2 lambda. Negative lambda multiplied by positive 2 is negative 2 lambda. Negative lambda multiplied by negative lambda is positive lambda squared minus 1 equated to 0. So this implies, so we have lambda raised to power 2. We have lambda raised to power 2. We have negative 2 lambda, negative 2 lambda will give you negative 4 lambda. Then 4 minus 1 is positive 3 equated to 0, right? So this is now a quadratic equation. Let's factorize, right? This is a quadratic equation. Let's factorize. So we need what? So first of all, let's use this constant to multiply the coefficients of this lambda with power 2. So 3 multiplied by, the coefficient of lambda with power 2 is 1. So 3 multiplied by 1 is 3. So we look forward 2 factors of this 3 such that their sum will give you the coefficient of this lambda at the middle. The coefficient of lambda at the middle is negative 4. So we need 2 factors of 3 such that the their sum will give you this negative 4, and their product will give you this 3, right? So those two factors will be negative 1 and negative 3. So because negative 1 plus negative 3 will give you what? You'll be having negative 1, negative 3 will give you negative 4. So, and if you multiply their product, it will give you positive 3. So this term, this negative 4 lambda, can be written as negative lambda, negative 3 lambda, right? So the coefficient of this lambda is this, negative 1. The coefficient of this lambda is this, negative 3. So this simply implies, so we have lambda raised to power 3, and this negative 4 lambda is this, negative lambda, negative 3 lambda, then plus 3 equated to 0. So this simply implies, so let's factorize this. Lambda is common, right? Lambda, then, so this is lambda square, sorry. Lambda divided lambda square, we have lambda. Lambda, we have minus here. Lambda divided lambda, we have 1. Then, what is common here? 3 is common. So, we have factor negative 3 into, so here will be lambda, and here will be negative 1 equated to 0, right? So this implies, so pick this and pick this, we have lambda minus 3, then pick one of these, lambda minus 1 equated to 0. So with that, we have done the factorization. So this simply implies that our lambda 1 is 3 and our lambda 2 is 1. So we have that this bracket multiplied by this bracket is giving you 0, right? So this simply means that this is 0 or this is 0, right? Lambda minus 3 is 0 or lambda minus 1 equals what? 0. That's what it means. So here, if you move negative 3 to the right, it will give you what? 3. Positive 3. If you move negative 1 to the right here, it will give you what? Positive 1. So the first lambda will be 3 and the second lambda will be what? 1. So I hope you understood it. So let's proceed. So what you are going to do is you are going to get the eigenvectors corresponding to each of the lambda. Let's get the eigenvector corresponding to lambda 1 equals 3. For the eigenvector corresponding to lambda equals 3, we will solve. So let's solve this. So to find the eigenvector corresponding to lambda equals 3, we will solve this equation. A minus lambda sub 1I multiplied by capital X equated to 0. So this is what we are going to solve. So you are going to put, basically the general formula is just looking like this: A minus lambda I capital X equated to 0. This capital X is the eigenvector corresponding to this to that very lambda. So that's why I wrote lambda 1 here instead of just lambda, because we want to get eigenvector corresponding to lambda 1, right? So that's why I wrote this lambda 1. So you use this. This is just the general formula. So I'm putting lambda for lambda 1 now. So with that, we can get our eigenvector. So this implies, so let's put our matrix A. Our matrix A is given on the board. So we put our matrix A, 2, negative, I have entry 2, negative 1, the other entry, negative 1, 2, minus, what is our lambda? If lambda 1 is what? 3. The identity matrix, we have identity matrix, then multiply by this capital X. This is just a column vector. I have entry x1, x2. So it stop at x2 because this our matrix A is 2 by 2, and it has how many columns? It has what? How many rows? It has 2 rows, right? So it has 2 rows. So that's why I have to stop at x2. So equated to this 0 will be column 0 vector or matrix. So this is what we have. So this simply implies, so we have our matrix A, 2, negative 1, negative 1, 2. So let's multiply. 3 multiplied by 1 is 3, 3 multiplied by 0 is 0, 3 multiplied by 0 is 0, 3 multiplied by 1 is 3. Then you have your column vector. You have weighted to the 0 matrix. So this is basically what we have. This is basically what we have. So what we are going to do, we are going to continue the solving here because no space there. So this simply implies, okay, let's just go straight and subtract. 2 minus 3, 2 minus 3, I have negative 1, negative 1 minus 0, negative 1, negative 1 minus 0, negative 1, 2 minus 3, we have negative 1. So this is what we got. Then this x1, x2 weighted to, this is what we have. So what we are going to do now is we are going to reduce this matrix. We are going to use roll operation to reduce it, so that we will now solve this equation. So let's reduce this matrix. Now this matrix, we can reduce it. Perform roll operation on it. Right? Let's perform roll operation on it. So the first non-zero, zero in any row is called the leading entry. So the leading entry of this row is this negative 1. So let me make it to be positive 1. Let me make it to a positive 1. How do we make it to a positive 1? Multiply it by negative 1. This, it will be positive 1. So we are going to say row 1 multiplied by negative 1. Right? So let's do that. If we multiply by negative 1, this, both of them will be positive 1. Positive 1. Right? Then, after the first non-zero of that row, that is the leading entry. Then every other thing below the leading entry. So the leading entry here is this. Then what is below it is this. So let's make it, you will make the what is below it to be what? 0. So how do we make this to be 0? To make it to be 0, you will multiply, if this one is positive, and add, when you do positive 1 plus negative 1, you get 0. So let's make this one to be what? Positive. And add it to this. So how do we make it to be positive? So what we are going to do is you multiply the first row by -1 and add the result to the second row. That's this one. That's what I wrote. -1 multiplied by first row, you add the result to second row. So let's do that. -1 multiplied by -1, +1. You add it to +1 plus -1, you get 0. -1 multiplied by -1, +1. Add it to this -1, you get 0. So this is what we have. With this, we have reduced this matrix. So our equation will be so we get what we are going to get here will be this. So this matrix, we have reduced it to be this. So we come here and put it. So if you put it, we will have, after it, have this column vector. This is equated to 0 vector or 0 matrix. So what I'm going to do is, we need to solve this. So for you to solve it, what you are going to check first is, you check whether each of the column has a leading entry of any row. Now the leading entry of the first row is the first non-zero number, which is this 1. After we have performed the operation, before it was reaching the matrix we had here, was leading entry was -1, but after performing the operation, the leading entry is now +1 in this new transform matrix. So now, what is this +1, which is leading entry, is located there at which column? Column 1. So x1 we are not going to call x1 a free variable. X1 is for column 1, this is x2. X1 is for column 1, x2 is for column 2. So x1, which is for column 1 has a leading entry of the first row. That is the first non-zero number in the first row, is located at column 1. So we are not going to call x1 a free variable. That is a constant, a real constant. Let me say alpha or beta. Now, if you come to row 2, they are 0. The entries are 0 throughout. So because of that, row 2 does not have a non-zero number, so it doesn't have a leading entry. Now, if you come to column 2, because of that, column 2 does not have a leading entry of any row at all. So this column 2 does not have a leading entry of any row. It doesn't have a leading entry of the first row. The second row the second row as 0 throughout, doesn't have any leading entry. So because of that, x2 is corresponding to column 2. Because of that, we are going to call, since x2 is corresponding to column 2 and column 2 does not have a leading entry, so x2 will be a free variable. So we are going to say let x2 equal to alpha. Well, this alpha will be element of real numbers because the entries of our matrix A are real. So because of that, we are going to use that to solve this now. If you want to solve it, do the multiplication starting from the last row. So x1 multiplied by 0 is 0, plus x2 multiplied by 0 is 0. 0 plus 0 is 0. You are having 0 equated to what? 0. So you did not get any value for x1 and x2. So let's go to the first row. So x1 multiplied by 1 will give you x1, plus x2 multiplied by 1 will give you x2, then equated to what? 0. So this implies, make x1 a such formula that your x1 will be equal to, move positive x2 to the right, we have negative x2. So which equals negative x2 is what? Alpha. So you will get negative alpha. So which means that x2 is alpha and then x1 is negative alpha. So your vector now, your vector having entry x1, x2 will be equal to your x1 is negative alpha, your x2 is alpha. So and this will be, let's choose a particular alpha because alpha is just a real number. So it can be 1, 2, 3, 4. So for simplicity's sake, we are not going to choose a fraction. We'll choose a whole number. So and the simplest whole number. Just let's choose 1. So here will be negative 1 and here will be positive 1. So at what? At alpha equals 1. So we choose alpha to be 1. So with that we got that very vector. So they will continue the solving for lambda equals, for lambda what? For lambda 2 equals what? 1, right? That's, you remember when we got our eigenvalues, we got lambda 1 to be 3 and what? Lambda 2 to be 1. For lambda 2 equals 1, we will solve this a minus lambda 2 I capital X equals to what? 0. So it is, we want to solve this to get what? The eigenvector, right? So this implies our matrix A, we have it on the board, minus our lambda 2 is 1, right? So we have 1 multiplying the identity matrix. So we have our identity matrix. Then we have our capital X, that's you have seen it in the other one we solved, that's x1, x2. Then 0 is the 0 vector or the 0 matrix. So this simply implies, so we can subtract, right? 2 minus 1 is 1. Negative 1 minus 0 is negative 1. Negative 1 minus 0 is negative 1. Then 2 minus 1 is 1. Right? With this we have subtracted. So we have our column vector x1, x2. Then we have the 0 matrix. So we are going to do the similar operation, matrix operation, as we did in the other one for this very matrix. So now this matrix, we can reduce it. This is just reducing it. We can reduce it. Then to reduce it, if you come to the first row, the first non-zero number is 1, right? That's the leading entry. So leading entry is always the first non-zero number. Then what is below it is what? Negative 1. So this negative 1 must be 0. What is below the leading entry must be 0. This negative 1 must be 0. So because of that, how do we make this negative 1 to be 0? If you add this positive 1 and negative 1, you're going to get 0. So simply we are going to say we are going to add what? We'll multiply row 1 by 1, right? And add it to row 2. Or just simply write row 1 plus row 2. So simply you can write that row 1 plus row 2. So let's add. If you add this, so we are going to have what? So let's write our row 1. Row 1 is this negative 1. So we add this. 1 plus -1 is what? 0. And -1 plus 1 is what? 0. So with this, we have reduced it. This same operation, this thing we did here, you can simply write it like this. You can write it like this. Row 1 multiply by +1, then add the result to what? Row 2. So we are multiplying by +1 because we don't want our row 1 to change, because we want to add it directly to row 2, so that +1 plus -1 can give us 0, so that this will be 0. So because of that, we multiply row 1 by +1 so that it will not change. Then add the result to what? Row 2. Row 1 multiplied by 1 multiply row 1, add the result to row 2. This is what we did. So we have reduced that matrix. So now, we have, so we are going to have, we replace this matrix with this in this equation. So we have this reduced matrix, then we'll have our column vector. So this is basically what we have. So we do the similar analysis we did in the other one. The first non-zero in the first row is this 1, this +1 here. Then and this +1 is located at column 1. I told you that x1 is for column 1, x2 is for column 2. So since it's located at column 1, so x1 will not be a free variable, because since x1 is for column 1 and column 1 has a leading entry of a particular row, in particular the first row, so it will not be a free variable. Now row 2, they are 0 throughout, so it doesn't have a non-zero number, so it doesn't have a leading entry. Because of that, it happens that this column 2 does not have a leading entry of the first row, it doesn't have a leading entry of the second row. So, and x2 is corresponding to column 2. So x2 will be a free variable, a constant. So let x2 be a free variable, alpha, a real number. Since our matrix A is real, the entries are real. So what we are going to do is, we are going to multiply, we are going to start from the last column. So x1 multiplied by 0 is 0, plus x2 multiplied by 0 is 0. 0 plus 0 is 0. So you have 0 equals 0. Did we get any value for x1 and x2? No. So go to the first row. x1 multiplied by 1 is what? Now x1 multiplied by 1 is x1. x2 multiplied by -1 is -x2. Then equated to what? 0, right? So this simply implies that x1, let's make x1 the solution of the formula. If you move -x2 to the right, you have +x2. So x1 equals x2. And what is your x2? We have called it alpha, a free variable. So let's make the statement here, free variable. No space here. So this is free variable. So I've made the statement here, free variable, right? So let's write what our column vector will be. Our column vector x1, x2 will be equal to, what is your x1? Alpha. What is x2? Alpha, as we got it here, right? So let's choose a particular alpha. Alpha is any real number, so let's choose a particular alpha. For simplicity's sake, we choose 1. So we're going to have 1, 1. So at where? at alpha equals 1. So our matrix P hence, let's make the statement here. Hence, our matrix P, the one we are looking for, will be equal to the first column will be the one we got for the eigenvector we got for lambda equals 3. What do we get? We got what? -1 and then +1. You remember what we got? For lambda equals 3, we got -1, +1, right? At alpha equals 1, right? This is what we got. Then for lambda equals 1, that's this one we have solved. What do we get? We got 1, 1, right? That is a column vector having entry 1, 1. For alpha equals 3, we got a column vector having entry -1, 1. So this one, we got a column vector having entry +1, 1. So this matrix P has been formed by what? Those two vectors has formed the columns of this matrix P. And this is actually what we have. So it is now, I can leave it as an exercise for you to verify that this matrix D, that this diagonal matrix will be equal to P inverse AP. That's the inverse of this matrix multiplied by A multiplied by P. Though this is not what we are to do in this question. Our work is to find this, and we have done it, right? So this matrix D, this diagonal matrix, will actually be formed by what? It will be formed by those two eigenvalues. So the diagonal matrix will be formed by the principal diagonal. We have lambda 1, lambda 2. Here will be 0, 0. Because your matrix A is 2 by 2 now, it will be 2 by 2 diagonal matrix. So this D is supposed to be in this form. Lambda 1, what was our lambda 1? 3. Lambda 2 was 1, so 0, 0. So you have to verify that this will give you this diagonal. P inverse multiplied by A multiplied by P will give you this. So thank you so much for being part of this class. See you in our next class. Thank you so much.